Welcome to this lecture on conservation of mass. We're going to be talking about the Reynolds transport theorem first of all in this lecture, and then we'll use it to derive conservation of mass, and then I'll say a few words about some things you should keep in mind when you apply conservation of mass for a problem. And as always, after this lecture, there are going to be some separate videos for example problems where we use conservation of mass, so I encourage you to take a look at those to see the actual applications. So let's go ahead and take a look at the screen. On the screen here, you'll see a picture of a cartoon of a fellow running in the rain. And I like this picture because I have an example problem that I'll do, again, in a separate video where we answer the question, is it better to run or walk in the rain? It's a very general question, and I like it because it's a good modeling question. We have to define our objectives more precisely, make the problem more well defined, and then the way we'll determine whether it's better to run or walk in the rain is we'll use conservation of mass. The idea is you want to minimize the amount of mass that you accumulate on your body as you run through the rain from point A to point B. And we can use conservation of mass to do that. If you look on your screen, there's actually a paper that's been written on this topic. It's given right down here, the link at the bottom. And there's actually been a Mythbusters episode, actually two of them, that take a look at this question as well. So I encourage you to take a look at those, do a search for Mythbusters running in the rain, and take a look at those videos too. But we'll analyze it from a fluid mechanics perspective in a separate video. So to get started, we'll first of all talk about something known as the Reynolds transport theorem. Now I'm going to have a separate video on this topic. It's not required that you watch it. It just goes through the derivation of it. I'm not so interested that you understand the derivation of the Reynolds transport theorem. But I'm going to present it anyway, just in case you're curious. But the Reynolds transport theorem is actually a critical tool that we use in our control volume approach. So we're getting into control volumes. Now we're going to do control volumes for conservation of mass, for the linear momentum equation. You can also do control volumes for the first law. We're not going to do that much in this course. That was more of a thermodynamics course. But fundamental to deriving these expressions for control volumes is the Reynolds transport theorem. So let me first start with a kind of a sort of an odd example, but you'll see where I'm going here in just a little bit. So let's say we're interested in studying birds. Okay, so let's say we want to study birds, and we can study them two different ways. One way is we can stand on the ground. So we draw a picture of us standing on the ground here. And we can watch birds as they fly overhead. Right, so these birds may be flying past. We can record how fast they're flying, what altitude they're flying at. If we have a pair of binoculars, we can record the color of the birds, maybe how big they are, that kind of information. But the idea here is that we're standing in one spot and we're taking measurements as things go past us. That's called an Eulerian point of view. Euler is a famous fluid mechanics person and also did a lot with mathematics. So it's called an Eulerian point of view. We'll call it a control volume point of view. So I'll put down here control volume as well. So that's one way we can study the birds. Now another way we could study the birds is we could capture a few of them and then tag them, put little radio collars on them, what have you. So here I'll draw my best attempt to draw a bird, and I'm not much of an artist. So here's a bird, that's supposed to be a wing, and there's a tail and a foot. And let's say we put a little tag on there, a little radio antenna. And we can do that to several birds and then track data for those individual birds as they fly along. Again, we can track what altitude they're at, how fast they're moving, how long they rest, that kind of information. It's another way to study those birds, but it's just a different technique that's being used. We call this a Lagrangian point of view. Lagrangian. Again, the name of a famous mathematician, fluid mechanics person, etc. This Lagrangian point of view is also called a system point of view. So in the Eulerian point of view, what we do is we look at a volume in space and study how material comes in and out of it. And in the Lagrangian point of view, what we do is we track individual quantities of matter that we're interested in this case birds, but we track individual elements and see what happens to them as time goes on. So two different perspectives that we can use. Now the reason I'm telling you all this is because it's easiest to formulate our governing laws in the Lagrangian point of view. For example, conservation of mass, which we'll talk about today. In a Lagrangian perspective, conservation of mass simply states that mass for a system is neither created nor destroyed. That if you have particular quantities of matter that you're tracking, little bits of fluid, their mass is always going to stay the same. No matter how they move around, they're always going to stay the same. We're neglecting nuclear reaction kinds of effects. We're not changing matter into energy or energy into matter. These are typical engineering situations. So it's very easy to state conservation of mass for a system. Mass is neither created nor destroyed, or the mass of a system doesn't change with time. You can do the same sort of thing for Newton's second law. In Lagrangian point of view, just the time rate of change of a system's linear momentum is equal to the net force acting on it. It basically simplifies down to F equals ma. It's very easy to write it for a system. However, it's hard to apply the governing equations to systems in practice. So, for example, let's take a look at the screen here. Let's say I have a jet engine, and we have air coming in and out of it. It would be hard to track individual bits of fluid, individual bits of air, individual bits of fuel, and then track those as they move through our, in and out of our jet engine. It's hard to keep track of individual molecules. It's really not practical. Instead, it's a lot easier to analyze a jet engine using an Eulerian perspective. If we drew a control volume that went around the engine, and we just looked at what goes into the engine, what goes out of the engine, how things are changing inside the engine, that's a much easier thing for us to analyze. So when we actually solve problems, it's much easier to solve those problems using an Eulerian perspective. So on one hand, we can derive our governing equations most easily from a Lagrangian perspective, but on the other hand, it's easiest to apply governing equations to control volumes or using an Eulerian perspective. So it'd be nice if we had a way to convert between the two different perspectives. And fortunately, we do have that tool, and that tool is called the Reynolds transport theorem. It allows us to write the governing laws in the Lagrangian sense and then convert them to an Eulerian sense, and then we can apply those to solve problems. So that's called the Reynolds transport theorem. I'm not going to derive it in this lecture. Like I said, I'll have a separate video in case you want to look at that. The derivation is not critical for you to know in this course, but it's there in case you're interested. It's also in many textbooks as well as my book style notes. But let me just write down what the Reynolds transport theorem looks like, and then we'll go ahead and apply it here in this lecture to derive conservation of mass for a control volume. So we take a look at the screen, and you can ignore that first line here. Recall the Reynolds. You know what? I'm going to rewrite it up here. Never mind. So let me write it out, and then I'll explain what the terms are. Oops. So it looks complicated, but I'll tell you conceptually what all the various terms are, and hopefully it'll make a little more sense. Okay, so this is the Reynolds transport theorem. And I'll abbreviate it as RTT. On the left-hand side, we have well, first of all, let me focus on this quantity beta. Okay, beta is what we call a transportable property. It's just some property that you can move from place to place. And it's actually the amount of that property per unit mass. So beta, let me write it down here. Beta is the amount of B per unit mass. And B, again, is some transportable property. B is meant to be something arbitrary. So what do I mean by a transportable property? Something you can move from place to place. mass is an example of a transportable property. You can move mass from one location to another. So in that case, B would be mass, and beta would be mass per unit mass, which would just be 1, right? Another transportable quantity might be linear momentum. Each fluid particle has some linear momentum, so we could move that linear momentum around. So in that case, B would be the linear momentum, mass times velocity, and beta would be linear momentum per unit mass, which would just be velocity. Another example of a transportable quantity might be the total energy of a little piece of fluid. We can move a piece of fluid around that has its own energy, and so in that case, B would be the total energy, and then the beta would be the energy per unit mass, or specific energy, specific total energy. So those are some examples where we could apply the Reynolds transport theorem. So B here is just meant to be some arbitrary quantity, and beta is that quantity per unit mass. So let me highlight in yellow here this quantity rho dV. Rho dV is just a little bit of mass, just density times a little bit of volume, so that's a little bit of mass. And then what we're doing is we're multiplying that by a little bit of mass by beta, so this gives me a little bit of B. So the idea here is we have some system, and we have a little piece of fluid here in our system that has a mass rho dV, and the amount of B we have there, dB, would be the beta, the amount of B per unit mass times the little bit of mass, or beta times rho dV. So that's for one little piece of fluid, the amount of B we have for that little piece of fluid, and then what we'll do is we're going to add it up, or integrate over the whole volume of the system. So we're going to do this over the whole volume of the system. So we're going to take each little piece of fluid and add up all the little amounts of B for each one. So we're going to do that over the whole volume of the system. So this integral then represents the total amount of B in the system. So again, if we were interested in mass, it would be the total mass in the system. If we were interested in linear momentum, it'd be the total linear momentum of the system. And then we have this time derivative. It's a funny looking one. I've written it with a capital D here, capital D dt. This is a notational item. The capital D just means this is a time derivative as we follow a system, rather than as we look at a control volume. It's just notational. It's kind of like partial derivatives versus ordinary derivatives. An ordinary derivative just means that when you take the ordinary derivative of a variable, it means that variable is just a function of one other variable, right? So if I had, for example, let me put this up here. If I had y was a function of x, then when I do dy dx, when I write that as an ordinary derivative, it just means that y is only a function of x. If I had dy dx as a partial derivative, what that implies is that y is a function not only of x, but maybe some other variables, maybe z and t and other stuff. It's a notational device that just lets us know that y is a function of more than one variable. The capital D dt here, again, is just a notational device to let us know that this is the time derivative as we follow a system. Okay? So we now know then that the d dt of B in the system, that's just going to be the time rate of change of B in the entire system. I'm going to move this out of the way. Okay, so the whole left side here is the rate of change of B in the system. So that's what the left-hand side says. Now the right-hand side looks much the same. The first oops, I missed a ddt here. In our first term here, we have the integral over the control volume. This is the total amount of B in the control volume. So let me just, it's only, the curly bracket on top is only concerning the integral. So that's the amount of B in the control volume. And so the ddt of that is the rate of change of B in the control volume. you'll notice that the integration occurs over the control volume. So just some region in space. Okay, so on the left-hand side, we have a volume of a system. The right-hand side, we have volume over a control volume. Again, the difference between a system is that it's a particular quantity of matter that we've chosen to study, just a bunch of molecules. And then on the right-hand side, it's a region in space. That's a control volume. So that first ddt over the integral is just the time rate of change of the total amount of B in the control volume. Then the very last term here, let me give myself some more space. This very last term, this is the net rate at which B leaves the control volume through the control surface. The idea here is, let's say we have some control volume and there's some fluid that comes in and out of that control volume, right? So every time fluid comes in, it brings some B with it, some new amount of B into the control volume. And then every little piece of fluid that leaves the control volume takes its amount of B with it. So that's this last integral over the control surface, the CS means control surface, is the net rate at which B is leaving the control surface. And so it takes into account stuff going out and stuff coming in. It's all taken into account together since it's the net rate at which B leaves the control volume through the control surface. The urel.dA, I'll talk more about what that is, but this represents a little bit of volumetric flow rate. So dq here is a little bit of volumetric flow rate. It's like velocity times area. It gives you a volume flow rate. When you multiply by a rho, that gives you a little bit of mass flow rate. So rho urel.dA is a little bit of mass flow rate. And then when you multiply it by beta, which is B per unit mass, then it gives you the rate at which B is leaving our control surface. The CS here is just meaning over the control surface. So the idea here is if we have a control volume, this last integral, the CS integral, is just right at the surface. The control volume is on the inside, right? So what we're doing is we're saying there's some little bit of area like that. So we'll call that area dA. And notice that A is a vector. If you look in the equation, we have dA is actually a vector. And the reason for that is every surface has some orientation to it. So let's imagine my hand is a little bit of area, has some magnitude, but we can put a normal vector on that area. And that way, even though we have a magnitude that stays the same, if I tilt it, the vector changes. So we have a normal vector, it's actually a unit vector, length of 1, attached to every area that gives it some orientation. And that unit vector will show as being n hat. So dA is just the magnitude, and I'll just write it as dA times n hat. That makes it the vector. And that normal vector, that unit normal vector, n hat, is an outward pointing normal vector. It points outside of the control volume. So if I drew another little area down here, its normal vector would be pointed out of the control volume that way. Now through that little bit of area, we can have some flow of fluid. Let's say the fluid at the control surface there looks like that. That's the velocity of the fluid right there at the control surface. Right at the surface, this is the velocity of the fluid as it comes out. Now, one of the things we have to be a little careful of is maybe our control surface is not fixed in space. Maybe it's moving or expanding and contracting or rotating or anything. When we choose control volumes, they don't have to be fixed. They're just some region in the space that we're interested in. We could have that region in space deform. We could have the region in space move. We can make it do whatever we want. So it's possible that the control surface could be moving. So let me draw that control surface vector in here just to keep it arbitrary. So there maybe the control surface is going that way. So I'll write it as UCS. So to get the velocity of the fluid since ultimately what this last integral is, if you look on the screen, this is the rate at which B is leaving the control volume through the control surface. What I really want is the relative velocity between the fluid and the control surface. If the fluid and control surface had the same speed going off to the side like that, then no fluid would come out of the control surface because the surface moves exactly at the same speed as the fluid, right? So I really want a relative velocity between these two. So UREL, I'll write it over here, UREL is the velocity of the fluid at the control surface minus the velocity of the control surface there. So that's what the UREL term is. It's a relative velocity of the fluid relative to the surface. Now you'll notice that in the equation here we have a dot product. It's UREL dot dA. So the reason we do a dot product here is because we only care about the component in the same direction as the area. So what we're doing is we're doing a dot product between the relative velocity and the area. Let me just kind of draw this somewhere else here to give us a little more space. So let's say this is a little bit of the surface. Here's our little bit of area. I'm going to draw it a little more three-dimensionally here. So let me try my best artistic skills. So let's say that our area looks like that with the normal vector this way. So this is our area dA. And let's say our relative velocity there, it looks like this. Okay, so that's the fluid velocity at the control surface minus the control surface velocity. And I'm just going to write it as UREL. What I want is the dot product of these two so that I get the component of the relative velocity command. So this is UREL dot dA. Or actually dot n hat. So that gives me the component of the velocity coming out through the area. Now why the dot product? Well, imagine then, let's say our area has this unit normal vector pointed straight up. And let's say our velocity is parallel to the surface, like what I'm showing here. In fact, let me draw it better on the screen. Let's say our normal vector is this way, and our relative velocity is that way. Well, if that's the case, if they're perpendicular to one another, then there's no fluid that's leaving the control surface, right? It's just going parallel or tangential to the surface. It's not actually coming out. The part that's coming out is the normal component. The part that's tangential to the surface never leaves the control surface. It's only the normal component that comes out. So that's why we're interested in UREL dot n hat. And if we want the volume flow rate, what we want to do is take the velocity normal to the surface, the velocity component coming out, and multiplying it by the area. And that gives me the rate at which volume is leaving the control, control volume through the control surface. So, if I let this go for a certain period of time, what would happen is it would sweep out a volume. So if I let this go for some period of time, we'd get a little volume element that looks like this. Everything on the inside here is the amount of volume that would be coming out through that area over some amount of time. So let me write that out. So the little bit of volume that's come out here is the relative velocity dot product with the n hat times the magnitude of the area, dA. That gives me the volume over a little bit of, actually let me change that. Instead of dq, let me just call it a little bit of volume, dV. And then I multiply it by a little bit of area. Give me a moment to move this out of the way. So if I let this go over some period of time dt, so that's the amount of volume that's been swept out. That purplish stuff is the amount of volume that's been swept out over that time t. And so the volume, the rate at which we're sweeping out volume, I'll write it down here, it would be just dV dt, which we call dq. That's our little bit of volumetric flow rate. And that'll be our UREL dot dA as a vector. So that's the little bit of volume that's been swept out. Again, if we multiply that by density, we get the little bit of mass flow rate. That's this bit in parentheses. And then when we multiply it by the amount of B per unit mass, that gives me the little bit of B that's left through that little bit of area. And when I integrate it over the whole control surface, I get the total amount of B that's left through our control surface. Now I say this is the net amount of B coming out. The reason it's coming out is when this dot product, urel.dA, is positive, it just means that stuff is coming out of the control surface. If the dot product is negative, then it means stuff is going into the control volume. So what we're doing is we're adding up over the whole control surface all the bits that are coming out and subtracting out all the bits that are coming in, and that gives us the net amount out. All right. It's a lot to absorb, so you're going to have to think about it a little bit, okay? So just to kind of refresh your memory here, the left-hand side is the time rate of change of our transportable quantity B within our system, and that's equal to the time rate of change of B in the control volume plus the rate at which B is leaving our control volume through the control surface. That's the Reynolds transport theorem. And when you look at that, you'll see on the left-hand side, that's a Lagrangian perspective, and the right-hand side is an Eulerian or control volume perspective. So this is the tool that allows us to convert between these two things. And again, if you want to see a little more mathematical derivation, there's a separate video you can take a look at for that. Let's go ahead and apply it so you can see how it's useful. And we'll apply it to conservation of mass. So here we are with a nice cleaned up version of the Reynolds transport theorem. And in our case, what we're particularly interested in is conservation of mass. So conservation of mass for a system, we'll write out. And it just says that the mass of a system doesn't change with time. And again, a system is like a particular quantity of molecules or atoms, right? Their mass doesn't change with time. It's always the same mass. Right, so that's conservation of mass for a system in words. Let's write it out in terms of mathematics. So it's just saying the time rate of change of mass of the mass of a system is 0. Mass of a system doesn't change, right? Let's use our little notational capital DDT thing here, since we're taking the time rate of change of a system. So I'll just rewrite that as capital DDT of the mass of the system. It doesn't change with time, right? So I think everybody hopefully is comfortable with that. Now, it's possible that the mass of the system doesn't, let me draw a picture of a system here. So here's some arbitrary system. The mass of this little piece of fluid might be a little different than the mass of that piece of fluid, right? They could have little differences in density. So the mass of that little bit is rho dV, and maybe the mass of that one is also rho dV, but maybe the rhos are different. Maybe the density isn't uniform through that whole system. So in order to take into account this variability, what I'm going to do is just add, when I write the mass of the system, I'm going to write it as an integral and add up all the little bits of mass in the system. So let's do that. So capital DDT of the integral over the volume of the whole system of rho dV is 0. So this quantity in the square brackets is just the mass of the system. I write it as an integral. It just gives me more flexibility, right? So that's our mathematical statement of conservation of mass for a system. But if you look at that for a moment, it looks very similar to the left-hand side of the Reynolds transport theorem. And in fact, if the quantity we're interested in is mass, so B, our transportable quantity, is mass, then beta would be B per unit mass, or mass per mass. So it would just be equal to 1. So if B is mass that we're interested in, then beta is B per unit mass, which in this case would just make beta 1. So the left-hand side of this would be d dt of volume of the system, rho dV. So you can see that the left-hand side of this Reynolds transport theorem Looks exactly like the left-hand side of what we wrote for conservation of mass. And in fact, that's equal to 0 from conservation of mass. So let's just put on the left-hand side of this equation that the ddt is equal to 0 there. Let me give myself a little more space. All right, so now we can use our Reynolds transport theorem to convert this to a control volume point of view. So we'll continue with the right-hand side. So right-hand side, we have ddt of the integral over the control volume. Beta, we said, was 1. We have a rho dv. Control surface, beta again is 1. urel dot dA. So that's using our Reynolds transport theorem. So let me rewrite this so it's a little bit cleaner. I'm going to just take the very left-hand side and then combine it with the Eulerian part, which is the right-hand side. So let's rewrite that. That expression is conservation of mass, I'll abbreviate it as COM, for a control volume, abbreviated as CV, or conservation of mass in an Eulerian perspective. So that's conservation of mass. And what we did is we first defined what conservation of mass was for a Lagrangian perspective. Then we used the Reynolds transport theorem and we converted it now into an Eulerian perspective. Let me tell you what each of these terms are in this equation just to make it a little clearer. So on the very first term, the integral over the control volume of rho dV, this is the mass in the control volume. So the idea here is if we have some control volume, so this is the control volume in here, we have all our little bits of mass, which are just rho dV, inside the control volume. So we're just integrating all those little bits of mass over the control volume. That gives me the mass in the control volume. So this is the time rate of change, or dmCv dt. It's just the rate of change of mass in the control volume. So that's what that term is. Let's go ahead and take a look at the second term. This term, remember, this is just a little bit of mass flow rate, a little bit dm dot, because urel dot dA, we said, was a little bit of volumetric flow rate multiplied by the density gives you a little bit of mass flow rate. And then when we integrate it over the whole control surface, this is the net mass flow rate out of, oops, I flipped some words here, out of the control volume through the control surface. That term, if you've had a thermal class before, you've seen this sort of thing before. What it is it looks like m dot over all the m outlets minus m dot over all the inlets. It's like the summation there means overall the different outlets. So you take all the mass flow rates going out, subtract all the mass flow rates coming in, and that's the same as this integral. We just write it as an integral because it just gives us more flexibility. Again, maybe the density varies over the surface. Maybe the relative velocities vary over the surface. It just gives us more flexibility. Okay? So that's conservation of mass for a control volume. Let me just rewrite it in a more algebraic form, just so that you're convinced it makes sense. What I'm going to do is write it first, just kind of the same way that I have it in the box up above. But let me move some terms around here. I'm going to take the net mass flow rate out and bring it to the right-hand side, so it's the net mass flow rate in. So, again, this is conservation of mass for a control volume. The equation makes sense. So take a look at this for a second. Let's say the mass flow rate coming in and the mass flow rate going out are the same, right? Let's say whatever we're bringing into our control volume, we're taking the same amount of mass out. So the right-hand side would be 0. Then it says that the mass inside the control volume doesn't change with time. It just stays the same. That makes physical sense, right? Similarly, let's say that nothing goes out, only stuff comes in. In that case, the mass inside the control volume should increase with time. Again, totally makes sense. Similarly, if there's no mass coming in, but there's only mass going out, then the mass within the control volume should decrease with time. All makes physical sense. So the equation that's boxed in here looks pretty mathematical, but it makes physical sense. It's something that you've probably seen before from thermo. It's just written in a more general form to give us more flexibility to deal with varying densities, varying velocities, and things like that. Okay? All right. Hopefully you're convinced by that. Let me just give you a couple more hints or a couple more notes before we end the lecture here. So note number 1. It's very important that you draw, oops, let me write it as a D here. Draw your control volume. When you apply conservation of mass, it's applied to a control volume. So you have to draw your control volume. It's part of using the equation. There are other reasons you want to draw the control volume. Number 1, the choice of control volume affects your analysis. If you use different kinds of control volumes, your results, what you're calculating will be different, okay? It's part of a communications effort as well. If you're going to show your analysis to someone else, they need to know what control volume you're applying conservation of mass to, so they can understand how you're applying the equation. It also helps you when you draw it out, because you'll make fewer mistakes if you can clearly see what it is you're analyzing. If you find that you're not comfortable drawing your control volume, you draw it lightly, maybe erase part of it, maybe draw 2 or 3 control volumes, that means you don't understand it very well, and that you should probably take a little extra time to better understand it. Now, how do you choose a control volume? That is a tough question. It depends on the problem you're trying to solve, and unfortunately I don't have an algorithm I can give you that works every time. Knowing what control volume to use comes with experience and practice, and just applying conservation of mass and other control volume equations in just different situations. You get better at it with time. You just have to keep practicing it. All I can tell you is, in general, you want to choose a control volume that helps you helps you analyze what you're interested in. So, for example, when we were interested in the jet engine, we drew a control volume around the jet engine because that's what we were interested in. It would make no sense to draw, if we were interested in the jet engine, it would make no sense to draw a control volume around a cloud, right? Because we don't care about the cloud. It doesn't have anything to do with the jet engine. So you want to draw a control volume around the thing that you're interested in. And then the other thing, a little bit of advice I have for choosing control volumes is choosing the control volumes. Choose a control volume that makes your analysis a little easier. So if you look at conservation of mass here, like this dot product, urel.da, it's often easiest to draw a control volume that cuts perpendicular to a velocity. And the reason you do that, and this is the normal vector for that area, it just makes doing the dot product easier because they're perpendicular to one another. You don't have to worry about any cosines of any angles. It just facilitates your analysis. So choosing your control volume to make, to keep it around what you're interested in, and also to facilitate the calculations. Those are the only 2 things I can really tell you just in general on how to choose control volumes. So just do a lot of practice and you'll get better at it. But always draw your control volume. The second item I'll mention is carefully evaluate that integral, the urel.da integral over the control surface. Just a couple of things to keep in mind with this. First of all, the urel is the urel at the surface. So let me redraw a control volume here. Remember, this is our control surface, this is our control volume. So what we're doing is we're analyzing what's happening at the surface. This is the relative velocity. It's at the surface. It's where the fluid is coming in or out at the surface. It's not what's happening inside the control volume, it's what's happening at the surface. That subscript here, CS, just means it's only occurring over the surface, over this yellow bit. You don't worry about what's happening on the inside for this integral. And just again, keep in mind that the relative velocity is the velocity of the fluid at the surface minus the velocity of the surface itself. If the surface is fixed, then it's just the fluid velocity, because the control surface velocity would be 0. But it's possible the control surface could be moving, so you have to be careful of that. And then the last little bit here is you have to be careful of your dot product. Just make sure you do the dot product. You know, if the area vector and the velocity, relative velocity vector are at angles to one another, maybe you have a cosine theta kind of term in there. If they're in the same direction, then the dot product will be just a positive 1, or you know, if they're in opposite directions, you'll get a negative sign. So just be careful in evaluating that integral. All right, I think that's all I really want to say about conservation of mass. Take a look at some of the examples that are given in separate videos. And as always, let me know if you have any questions.